Welcome to Future Epoch, where we learn more about our world. Water covers 71% of this planet. That number is cited so often, it has lost its power. But here is the detail that matters. Of all the water on Earth, less than 3% is fresh, and most of that is locked in glaciers, ice caps, and deep aquifers that humans cannot practically reach. The water available for drinking, farming, and industry represents a fraction of what the planet holds. Right now, more than 2 billion people live in countries experiencing high water stress. Rivers that fed civilizations for millennia are running dry. Aquifers that took thousands of years to fill are being emptied in decades. And global demand for fresh water continues to rise as populations grow, cities expand, and agriculture intensifies. For a long time, the solution seemed impossible. The ocean holds an almost incomprehensible volume of water, but it is laced with salt at concentrations that make it undrinkable and lethal to crops. To use it, you have to take the salt out. And doing that at the scale modern civilization requires has been one of the great engineering and economic challenges of the 21st century. Desalination is the process of removing dissolved salts and minerals from seawater or brackish water to produce fresh water suitable for human use. The concept is ancient. Sailors boiled seawater for centuries. But turning a survival technique into an industrial process capable of supplying cities, industries, and entire nations is a modern achievement. Today, the global desalination industry produces around 100 million cubic meters of fresh water every single day, drawn from more than 21,000 plants operating across the world. That sounds enormous. In reality, it accounts for roughly 1% of global freshwater supply, serving around 300 million people. The gap between what desalination currently provides and what a water-stressed world may eventually need is the central challenge that engineers, governments, and investors are now trying to close. The modern desalination industry has its roots in the oil-rich nations of the Middle East. In the 1950s and 1960s, countries like Kuwait and Saudi Arabia sat on vast wealth but almost no natural fresh water. They had the energy to run energy-intensive plants, so they built them. Early facilities used a process called multi-stage flash distillation, which works by heating seawater until it evaporates, then condensing the steam into fresh water, leaving the salt behind. These plants were expensive to build and expensive to run, but in a desert with oil to spare, cost was not the binding constraint. By the 1990s, a fundamentally different technology had matured: reverse osmosis. Instead of boiling water, reverse osmosis uses high pressure to force seawater through specialized membranes so fine they block salt ions while letting water molecules pass. It is far more energy efficient than distillation, and as membrane manufacturing improved and costs fell, it transformed the economics of the entire industry. Israel became the most instructive case study. A small country with essentially no significant river system and subject to chronic drought, Israel built the world's most advanced national water system around desalination. By the 2010s, plants at Ashkelon, Hadera, Sorak, and along the Mediterranean coast were together producing the majority of the country's municipal water supply. The cost of desalinated water in Israel fell below 50 cents per cubic meter, a figure that would have seemed impossible 20 years earlier. Saudi Arabia scaled in a different direction entirely. The Saline Water Conversion Corporation now operates some of the largest desalination complexes on the planet. The Ras Al Khair facility on the Persian Gulf is among the largest seawater desalination plants ever built, producing over 1 million cubic meters of fresh water per day. In a country with almost no natural fresh water, desalination is not a backup option. It is the primary water infrastructure. By the 2020s, projects were moving beyond even this scale. Saudi Arabia's NEOM development, the ambitious new city being constructed in the northwest of the country, has committed to water infrastructure designed to operate entirely on renewable energy. The vision is desalination powered by solar and wind, eliminating the carbon cost that has long been attached to the industry. It is the most visible example of a broader trend. the push to decouple desalination from fossil fuels entirely. The fundamental tension in desalination has always been energy. To remove salt from seawater, you have to push water against enormous pressure through fine membranes or evaporate it entirely, and both processes demand significant electricity. Even modern reverse osmosis systems, which recover much of the energy used in pressurization, typically require between 3 and 10 kilowatt-hours per cubic meter of water produced. At the scale of millions of cubic meters per day, that energy demand becomes substantial. And for most of the industry's history, that energy came from fossil fuels, meaning that solving one resource crisis was contributing to another. The second major challenge is what gets left behind. For every liter of fresh water extracted from seawater, roughly 1 to 1.5 liters of highly concentrated brine is returned to the ocean. This hypersaline discharge is denser than surrounding seawater and sinks toward the seafloor near outfall points, where it can damage benthic ecosystems by reducing oxygen levels and harming marine species that cannot tolerate elevated salinity. The global desalination industry already discharges an estimated 142 million cubic meters of brine every single day, and that figure will rise as the industry expands. There is also the question of who benefits. The countries currently most dependent on desalination are, almost without exception, wealthy oil-exporting states or economically advanced nations like Israel and Australia that can afford the capital investment and ongoing operational costs. Sub-Saharan Africa, South Asia, and parts of Latin America face severe and worsening water stress, but lack the grid infrastructure, available capital, and institutional capacity to build large-scale desalination systems. The technology exists. The economics do not yet work for the places that need it most. Despite these challenges, the trajectory of the industry points toward continued and rapid expansion. The World Bank has identified desalination as a critical component of water security planning for water-scarce regions across the world, and global installed capacity has roughly doubled every decade since the 1980s, with no sign of that growth slowing. The integration of renewable energy is fundamentally changing the calculus. Solar power in the Middle East, North Africa, and parts of Australia is now cheap enough that renewable-powered desalination can approach cost parity with conventional fossil fuel-powered methods, and in some projections exceed it. Chile is pursuing solar-powered desalination to supply water to coastal mining operations in the Atacama Desert. Spain, which already operates large plants along its southern coast, is investing in further capacity as drought conditions worsen across the Iberian Peninsula. Energy recovery systems have also improved dramatically. Modern large-scale reverse osmosis plants capture and reuse a significant portion of the hydraulic energy from the pressurized brine stream, improving overall efficiency to the point where some new facilities report energy consumption as low as 2 kilowatt-hours per cubic meter, approaching the theoretical minimum for the process. Better membrane materials, more efficient pump designs, and smarter system management through digital monitoring are each pushing performance further. The geopolitical dimension is significant. Nations that can guarantee domestic water supply through desalination achieve a form of strategic independence that those dependent on rivers, rainfall, or overdrawn aquifers cannot match. As climate change intensifies droughts and alters precipitation patterns, the ability to produce fresh water from the sea, regardless of rainfall, may become a genuine national security asset. Conversely, regions that remain dependent on shared river systems face increasing tension as upstream nations divert water for their own use, a pressure that desalination does not resolve for landlocked populations. What this story reveals is that desalination is not a silver bullet. It is a powerful, proven, and increasingly affordable technology that already sustains hundreds of millions of people and which could sustain hundreds of millions more. But it is also a technology with genuine constraints, energy demand, brine disposal, cost, and questions of geographic equity that engineering alone cannot resolve. The most important shift underway is the move to pair desalination with renewable energy at scale. If solar and wind can power the membranes and pumps without carbon emissions, the energy objection weakens considerably. Brine management technology is also advancing, including processes that extract commercially valuable minerals from concentrated discharge, potentially turning a waste stream into a revenue stream. And costs have fallen far enough that the question is no longer whether desalination can work, but who will choose to invest in it and where. Water scarcity is not uniform. It is intensely local, shaped by geography, climate, infrastructure,